Welcome everyone. This is going to be our third video on Chapter 12, talking about intermolecular forces and liquids. So we just talked about the types of intermolecular forces we have, right? Ion dipole forces, hydrogen bonding forces, dipole-dipole, and London dispersion forces. Okay, right? These are listed in terms of increasing strength as you go up or decreasing strength as you go down this list, right? London dispersion forces occur in all molecules, right? And they are most significant in non-polar molecules, right? If you have polar molecules, you have other types of intermolecular forces that are much stronger and will be more relevant. Okay? Dipole-dipole forces occur between all polar molecules. Hydrogen bonding occurs only in molecules that have OH, NH, or HF type bonds. And ion dipole forces, right, occur between an ion and a polar molecule, right? So if we want to try to identify these things, okay, so this is kind of the flow chart I follow usually when I'm trying to identify the type of intermolecular forces, right? This is ignoring ion dipole forces. Ion dipole forces, right, you got to have an ion in your system. If you have an ion in your system, it's probably ion dipole forces, right? So just kind of throw that out and not worry about it. It simplifies the flow chart a little bit. Okay, so here the first thing we ask ourselves if we're trying to identify what is the dominant, the strongest intermolecular force that exists in this molecule, I first ask myself, all right, is our hydrogen atom bonded to nitrogen, oxygen, or fluorine? If yes, then it's probably got hydrogen bonding, right? Next, I'll ask myself, okay, if there's no hydrogen bonded to those atoms, okay, then do I have polar bonds that are asymmetrically arranged? If yes, then I have dipole-dipole interactions. If no, then I have these dispersion type interactions. Okay? And so this is typically the flow chart I follow and try to identify what type of intermolecular forces are most relevant in the molecule. Okay? And in class, we'll do lots of examples of these things to try to get lots of practice in identifying what are the strongest type of intermolecular forces between different atoms and molecules. Okay. So a little bit about understanding these intermolecular forces and how they affect physical states and physical properties of our molecules, right? First talk about our vapor pressure, okay, because it's related with our boiling point, as we'll talk about in the next few slides, okay? So what is vapor pressure? So vapor pressure exists as the pressure of a liquid that is going to exist in some type of closed container at equilibrium. Okay, so in this figure here, the idea that we have is you have this flask that has nothing in it. You then pour in some liquid, right, and then you seal off the flask. Okay, so right, the second middle part of this flask here, or this figure, right, has this flask where I've added the liquid into my flask and now I've sealed it off. Okay. So this is a closed system, sealed, right? Well, what happens in that flask is you have a bunch of molecules in the liquid phase, right? We just dumped in a bunch of liquid, so you got a bunch of molecules in the liquid phase, right? Well, at the surface of this liquid phase, you got a bunch of molecules moving around, right? One molecule might get kind of bumped or nudged, right, and get kicked off into the gas phase, right? It's got some amount of kinetic energy, right? It might get hit by some other molecule with kinetic energy and get knocked out into the gas phase. And now this thing has escaped the intermolecular interactions between other ethanols and it's just floating around in the gas phase, right? So it's now just floating around, moving freely in the gas phase, and this keeps on happening, right? At the surface, you've got more and more molecules that keep on getting kicked off into the gas phase, right? Well, in a closed container, right, those molecules are eventually going to hit the surface of your liquid again, right? Well, when they hit the surface of the liquid, they could just bounce off and keep going in the gas phase, or they could get reabsorbed into the liquid phase, right? And so what happens is eventually, right, the rate of which your molecules are getting kicked into the gas phase equals the rate of which the molecules are getting added back into the liquid phase. And so eventually you have a stable, equilibrated point, right, where you have some set of molecules in the gas phase that are just in that gas phase, right? And those number of molecules in that gas phase exert some type of pressure, okay? And that pressure is related to the vapor pressure of that liquid, okay? okay? And every liquid has a vapor pressure, right? Every liquid has some pressure it exerts in a closed container if you just pour it into that container, okay? Right? So again, just kind of summarizing these points, right? Vapor pressure, right, is the pressure exerted by a liquid in some type of closed container, right? And it's related with this dynamic equilibrium between a gas phase and a liquid phase of that material, okay? You increase vapor pressure by increasing temperature, okay? That vapor pressure is related with temperature, okay? And more volatile substances, right, will have higher vapor pressures, which means they evaporate more easily, okay? And a volatile substance, right, if you recall, right, something is more volatile, liquids are more volatile if it has weaker intermolecular forces, okay? Right? And so again, you can think of having some type of like oil, right? Some gasoline spilled on a surface, right, on the ground versus a puddle of water, and that oil, that gasoline will evaporate much, much faster than the puddle of water, right? And that's because it's more volatile, okay? If something's more volatile, that means that if you put it in a closed container, it's going to have a larger vapor pressure, okay? Because it wants to evaporate, wants to go into the gas phase because it's more volatile. So it's going to have a larger vapor pressure, okay? So the plot here is a bunch of different substances, okay? Diethyl ether, ethyl alcohol, water, ethylene glycol, right? A bunch of different substances, right? And their vapor pressure versus temperature, okay? And there's a dashed line at the top here, okay? This dashed solid line at the top is related with the atmospheric pressure, okay? So up here at the top, this line here is related with our atmospheric pressure. This is 1 atmosphere, okay? 1 atmosphere in torr is around 760 torr, okay? Right? And this is giving you, okay, the boiling point of these systems, okay? So the boiling point occurs, right? For example, we know water boils at 100 degrees Celsius. Well, it boils at 100 degrees Celsius because at 100 degrees Celsius, the vapor pressure of water equals atmospheric pressure, okay? So that is the point when a substance boils, is when its vapor pressure equals atmospheric pressure, okay? So, right, so diethyl ether boils at a much lower temperature because at a lower temperature, its vapor pressure equals atmospheric pressure, okay? Right, at 34.6 degrees Celsius, the vapor pressure of diethyl ether equals atmospheric pressure, okay? And that's because it's a more volatile liquid, so it has a higher vapor pressure, okay?